Okay, so I said that I was going to post a video from a few years ago as a derivation for the transport equation. I saw the video. I didn't like it for a number of reasons. Primarily, it's just vanity. Even though it was 2 years ago, I looked like I was 10 years younger. So I don't know. But the primary reason, that actually is not the primary reason. The primary reason is just that I think I was using different variables then that I'm going to be using now. I was still screencasting and the screen was very laggy, and so it just kind of is distracting that way. So I'm just going to rederive it here. So it's going to be very generic because what we want to do is we want to imagine there is some one-dimensional thing. It could be a pipe. Again, we're just going to assume infinite length here. It could be a pipe with water flowing through it. It could be a road with cars flowing through it. And we want to model some quantity. So U, let me see where I can write this. U is equal, U of xt is equal to concentration of something. I'm going to say concentration of a substance. So concentration of a substance, whatever that substance may be. And for right now, it could be any type of substance at all. It could be dye flowing in a water pipe. It could be pollution flowing down a river. It could be the number of cars, per mile. And so the units here are going to be, example units are going to be things like kilograms per meter if we're measuring the pollution in kilograms. Or if we're measuring the dye in, like liquid measurements, maybe it could be ounces per foot. Or if we're dealing, this is a road and we want to look at cars, it could be cars per mile. Okay, so any of these will work. And so one of the basic things we're going to start with is something that we've seen so far. If I look at a generic point A and a generic point B, what does it mean when we say U is a concentration? It means at any time, the amount of substance, whatever that substance is between points A and B, is going to be the integral from A to B, U of xt dx. And just as we have done many times before, Q prime of t, well, if I take the derivative on the outside, I can push it onto the inside here. And it's going to now be the partial derivative of u with respect to t, xt dx. Okay. Produce a new quantity called f. Now, f is going to be equal to the units of substance flowing to the right per unit time. So F is the units of substance flowing to the right per unit time. Now there's only one spatial dimension, so F is a scalar, but we really should be thinking about it as a vector because it's like the flux. And I want us to have that conceptually that it's a vector, even though it's really just going to be a scalar. And I say to the right, so if it's a negative number, that means to the left. Okay, so it's units of substance flowing to the right per unit time. So what this means is that in this little interval here, so another way to compute Q prime of t, for this interval here, it's going to be rate in minus rate out. Well, the rate in, again, if we have rightward flow, the rate in is going to be at A, and the rate out is going to be at B. So it's rate in minus rate out. And again, if f of A is negative, it's going to be pointing that way, but the equation still works out. Just think through this, why rate in minus rate out is always going to be f here minus f there. So Q prime of t is going to be f of AT minus f of BT. And by the fundamental theorem of calculus, this is equal to the integral from a to b minus the x derivative of f dx. Now, this is a very familiar equation. This is just a conservation law. We've seen this exact equation when we looked at the diffusion equation. And so what we get, if I name some variables over here, if f I'm just going to call it flux now, but it means that over there, well, these two integrals are equal. Q prime of t is equal to that, Q prime of t is equal to that. Just as we've seen before, a and b are arbitrary. So what this gets us is that the t derivative of u is equal to minus the x derivative of f. Okay, and so now the question becomes, this is a differential equation in two unknowns, u and f. So what are we doing here? We need some third equation that some second equation that ties these two together. And we're always going to start with this, whatever our application is going to tell us how f and u are related to each other. Here's one example. If we stick in the example of there's water, flowing down the pipe here, and let's say we put in some wood, like we throw in some wood chips, and we just want to see how these wood chips are going to flow down this pipe here. Here's how we can relate f and u together. So let's assume if the velocity of the ambient fluid that is, if it's like wood chips in water, it's the fluid of that flowing down. The velocity of the ambient fluid is v of xt, and again, I'm going to make v a vector. It's conceptually it's a vector. You just have one spatial dimension, so it's only a scalar. But I want to think about it conceptually as a vector. If the velocity of the ambient fluid is v meters per second, or whatever our units are, then f is going to be equal to v times u. Okay, and we can do a little dimensional analysis here just to sort of do a sanity check. So the dimensions of f are going to be kilograms per second. The dimensions of v times u, well, what are we going to get here? That looks like a letter that doesn't exist. The letters of v times u, or the dimensions of v times u, the dimensions of v are meters per second. The dimensions of u are kilograms per meter. And so we get kilograms per second, which is what we needed. Okay, so let's plug this in over here. Let's assume we know, for example, that f is equal to v times u. So in this case, what we're going to have, if we rewrite this a little bit, to begin with, we're going to have the t derivative of u plus the x derivative of f is equal to 0. And this is now the t derivative of u plus the x derivative of v times u is equal to 0. Okay, so there's a number of things that we can do here. So by the way, in higher dimensions, this is going to be the gradient operator and not the derivative operator, or sorry, not the gradient, the divergence operator here, the triangle. So using the sort of the vector product rule, this is going to be u times the x derivative of v plus v times the x derivative of u equals 0. Now notice what happens if the x derivative of v is equal to 0, this term goes away, and we're just left with these outer two terms here. This gives us something like the t derivative of u plus v times the x derivative of u is equal to 0. This is called this equation right here is the one that is typically called the transport equation, though we can have these first order differential equations in various degrees of generality that we can look at. But the bottom line is, we start with something like this, or we get to something like this. This is called a conservation or a continuity equation, and then we have to somehow connect F to U. And the way we connect F to U is going to depend on what the exact scenario is that we're modeling. I've given one example here. When we look at cars, we're going to see a different example. It is sort of I'll explain it once we get there. It's going to be a different example than this. When we, if we were modeling other things, we would connect these in different ways. One thing to mention, though, is when we were looking at the diffusion equation, you might remember that I talked about this, about a quantity in a river or something, and I said we're assuming that the river is not moving, okay, but the quantity is diffusing. Here it's the opposite. We're assuming the river is moving, but we're not really assuming that the quantity is diffusing. That's why I use the example of wood chips, right? If you just take some wood chips and throw them into water, if the water is still, the wood chips don't like spread out from each other, like typically, like you would if you dropped dye or something. However, if the water is moving, and if you have this pile of wood chips, maybe the water speeds up here, so it's going to stretch it out here, and stuff like that. That does happen with wood chips. Or if it's like maybe dust particles going through a venting system, something like that. Okay, so this is a motivation for the type of first order differential equations that we're going to be studying. In the next video, I'm going to show a very, very basic first order linear differential equation, just to show how we're going to solve these differential equations. And then the video after that, I'm going to show a very generic first order linear equation, and it'll even mention quasi-linear equations. I will go through the outline of how we're going to solve those, and then the videos after that, we're going to apply that outline to successively more and more difficult and intricate problems. And like I said, I hope it's something that you're going to enjoy thinking through, and it's going to be really cool, I think, when we get to the quasi-linear stuff. Next week, we're going to see a lot of phenomena with differential equations that you have probably not seen yet.